Conservation of energy is one of the most important and fundamental concepts in physics. In this case, we're going to be talking about the conservation of mechanical energy, and then we'll deal with conservation of total energy. For starters, the total mechanical energy of a system remains constant as long as there is no friction or air resistance. To be able to understand this law, we have to understand what mechanical energy means. Mechanical energy, I'll just use an M period, E period to symbolize that, is equal to the total kinetic plus the total potential energy of a system. Sometimes an object will only have kinetic energy. Sometimes it'll only have one of the types of potential energy, but other times it could have all two or even three types: kinetic, gravitational potential energy, and elastic potential energy. Saying that it's conserved means that it's the same everywhere. So that means that the initial mechanical energy is equal to the final mechanical energy. We'll see how that plays out in a few problems. If for some reason we do have friction or air resistance present, total energy is still conserved, which means that the total initial mechanical energy is equal to the final kinetic energy plus the change in thermal energy, which is the type of energy that comes about from friction. That change in thermal energy can be calculated by the work that is done by friction. We know how to find the work done by a force. It's force times displacement times the cosine of theta. So if your problem has friction or air resistance, you simply need to find the work that's done by friction, and then you can use conservation of energy concepts. One last important thing to note is another way of saying conservation of energy. So I can say that the change in kinetic energy is also equal to the negative change in potential energy. That's just another way of saying the conservation of energy. When we're doing conservation of energy problems, it's useful to have some steps to follow. So here's a list of 5 steps for solving conservation of energy problems. I suggest that you pause the video and write down these 5 steps, and make sure that you bring these with you to class tomorrow so we can see them using with problems that we'll be doing. Great, now that you have these 5 steps written down, let's move on to seeing how to use these 5 steps in a problem. This problem focuses on a roller coaster at Kings Island, the Beast. The tallest hill on the Beast is 34 meters tall. We want to know how fast the riders are traveling at the bottom of the hill, assuming that they start from rest at the top and that friction is negligible. Of course, assuming that friction is negligible is really not an accurate assumption, especially if you've ridden this roller coaster before. But to make our lives a little bit easier, we're going to make that assumption. So if we step 1 here, it says that we have to define the system and verify the absence of friction. In this case, our system is going to be our riders traveling in their roller coaster vehicle. And the problem tells me that friction is negligible. So that's great. I know that I don't have to worry about friction in this problem, so I can focus just on mechanical energy. Step 2, choose a reference level. To choose this reference level, it's a lot easier to actually draw a diagram. So here's the top of my hill, and here's the bottom. You don't have to be overly artistic to successfully complete these problems. Just as we talked about in class, when we're doing a reference level, we're going to use a dashed line showing where that reference level is. And in this case, I've chosen the bottom of the hill because that's the lowest point that our roller coaster car can travel. A lot of times I'll draw the dotted line, and then I'll also write somewhere near it that that's the place where gravitational potential energy is 0. If you don't draw a diagram, since sometimes you don't absolutely need to do that, somewhere off on the side you should indicate where your reference level is located. Step 3, identify 2 points, one with given information and the other where you want to find information. So I'm told how high that hill is. That's this height here. 34 meters. Since I'm given information at that point, I'm going to call this my initial point. And then it's asking how fast the riders are traveling at the bottom of the hill. Since this is a point where I'm looking for information, this will be my final point. 4, write out the conservation of energy equation and identify the unknown quantity. In this step, which is probably one of the most important steps, we need to figure out what type of energy each object or our object has at each point. For starters, let's list the types of mechanical energy it could have. So it could have kinetic energy, it could have gravitational potential energy, and it could have elastic potential energy. It could have these types of energy at each point. Then I'll go through and cross out any types of energy that my object does not have at these points. For example, at my initial point, it says, assuming they start from rest. So if it's not moving, kinetic energy is 0. I also notice that I don't have a spring anywhere in this problem, so we're not going to be dealing with elastic potential energy. At the bottom of my motion, my car is at the reference level. That means gravitational potential energy is 0. So I'm left with the fact that initial gravitational potential energy is equal to final kinetic energy. Now, if you can look at the problem and just come up with this equation without having to write out the big long thing I started with, that's totally fine. But if you find yourself stumped, this equation that lists all the types of mechanical energy is a good place to start. Step 5 is to solve for the unknown quantity using variables and then plugging in numbers. So I'll start with that by plugging in my expressions for gravitational potential energy and kinetic energy. We know gravitational potential energy is mgh, and that's an initial height. And kinetic energy is 1/2 m v final squared. You'll notice in the problem we weren't given mass as one of our known values, and that's an okay thing, because if I divide both sides by mass, I find that mass cancels out. Velocity is the thing I'm looking for, so to solve for velocity, I'll multiply both sides by 2, and then I'm left with final velocity squared, and so I'll take the square root. So that final velocity is the square root of 2 times g times the height. I plug those numbers in my calculator. I find that this is going at 25.8 meters per second, which is a reasonable speed for a roller coaster car at the bottom of its largest hill. So again, looking over this process that we followed, we verified that we didn't have any friction, so we knew that we could do conservation of mechanical energy. We set our reference level to be the bottom of the hill. And then we looked at what type of energy we have at each point, plugged in equations for those types of energies, and solved for our unknown quantity. We'll have lots more practice doing this in class.